Welcome to the deep dive. Today, we're going to be tackling online learning.
Oh,
It's this really fascinating way that computers can analyze data that changes over time.
yeah.
And you sent us this paper called Gradient Equilibrium in Online Learning Theory and Applications.
Right.
And we're here to try to make sense of it all.
Absolutely.
You can think of online learning as making predictions, and you're always adapting to new information as it comes in. So it's kind of like
Yeah.
predicting the weather,
Well,
as
yeah.
as each day's data comes in.
Yeah, like a weather forecast that updates every minute.
Exactly, yeah.
Yeah.
And we're going to focus on this idea of gradient equilibrium,
Okay.
which is a key concept in this field.
It's really important.
And we're going to see how it can help make those predictions even more accurate.
Absolutely.
Right.
What makes online learning so powerful is that it can handle real-world data
Okay.
without having to rely on these fixed assumptions about the future. Like it's always updating its knowledge as new information comes in.
So it's not like those kind of old school methods
Right.
where, they assume that everything follows like a nice predictable
Exactly.
pattern.
Yeah, it embraces the unexpected.
Okay.
It acknowledges that things change.
Okay, so how does this gradient equilibrium
Yeah.
fit into all of this?
Mm.
The paper's introduction mentions minimizing the average of gradients over time.
Okay.
What does that even mean?
So think about it this way. Instead of trying to make the absolute best decision at each step,
Okay.
gradient equilibrium is about finding the settings for your learning algorithm so that on average, it's making the best possible adjustments over time.
So it's kind of like
Yeah.
finding this balance point.
Mm-hmm.
It's kind of like a tightrope walker, making these tiny adjustments to stay upright.
Yeah, that's a great analogy.
Okay.
Now, here's where things get a bit interesting.
Okay.
The paper makes a distinction between no regret and achieving gradient equilibrium. So no regret means you perform as well as the best fixed choice in hindsight,
Okay.
knowing what you know now.
So like having a crystal ball
Yeah.
and always making the perfect decision,
Exactly.
that's not realistic.
Not usually,
No.
in most situations.
And what's really cool is that the paper shows that you don't need no regret to actually reach gradient equilibrium.
Okay.
Even if you don't always make the absolute best choice, you can still find this balance point for your overall strategy.
So even if I don't make the perfect decision every time,
Right.
I can still have a good long-term
Exactly.
strategy.
Yeah.
That's a relief.
Yeah.
But how does an algorithm actually find this balance point?
That's where these restorative loss functions come in.
Okay.
They kind of guide the online learning algorithm toward equilibrium.
Okay, so restorative loss functions.
Yeah,
Those sound pretty important.
they're very important.
Can you give me an example of what one of these functions might look like? So imagine you're trying to train an algorithm to predict housing prices.
Okay.
A restorative loss function
Yeah.
might penalize the algorithm more heavily when it overestimates the price of a house
Okay.
compared to when it underestimates.
Okay.
So this would encourage the algorithm to err on the side of underestimation,
Okay.
which might be desirable.
So it's like a bias towards caution.
It is.
That makes sense.
Yeah.
Now, I know a lot of people are concerned about bias in machine learning models.
Yeah.
How does gradient equilibrium relate to that?
So that's a really important point.
Yeah.
Bias is a serious issue,
Yeah.
and gradient equilibrium offers a potential solution.
Okay.
The paper shows how this concept can be used to correct for bias in these models.
So instead of just scrapping the model and starting from scratch,
Yeah.
you can actually use gradient equilibrium
You can adjust it.
to adjust it on the fly.
Yeah, it acts as a fine-tuning mechanism
Okay.
to counteract the effects of bias in the data.
And this has huge implications for all sorts of areas like, healthcare and lending.
Absolutely.
Yeah.
Where biased algorithms can have real-world consequences.
Wow.
Yeah,
That's really powerful.
it is.
So gradient equilibrium isn't just some theoretical
Right.
concept.
It can make things more fair.
It can actually make these systems more fair and equitable.
Yeah, and we're just scratching the surface here.
Yeah.
There's so many applications of gradient equilibrium in all sorts of fields.
Okay.
Yeah.
Wow, this is fascinating stuff. So before the break, we were talking about how this concept can help address bias in machine learning models.
Yeah.
I'm really curious to hear more about that.
Of course, one of the key ways gradient equilibrium helps debias predictions is through the use of different types of loss functions.
Okay.
We've already talked about restorative loss, but there's also quantile losses and logistic losses.
Ah, yes, loss functions.
Yeah.
I remember them from the paper.
Yeah.
But to be honest, they sounded a bit intimidating. Can you kind of break them down for me and for anyone else listening who might not be a machine learning whiz?
Absolutely. Think of loss functions as a way of measuring how off an algorithm's prediction is.
Okay.
And different loss functions are designed for different situations.
Okay.
Like, for example, quantile losses are really great when you want to understand a range of possible outcomes, not just like the single most likely one.
So instead of asking, like, what's the most likely price of this stock tomorrow,
Right.
I might use a quantile loss to ask, like, what's the range of prices I should be prepared for?
Exactly.
Okay.
And in the context of debiasing, quantile losses can really help ensure that predictions are fair across different groups.
Okay, can you give us a concrete example of how that would work?
Sure. So let's go back to that example of a model predicting loan approval rates.
Yeah.
If there's bias in the data,
Mm-hmm.
the model might systematically underestimate the approval chances for a certain group of people.
Okay.
Using a quantile loss during online learning helps calibrate the model's predictions, hopefully to make sure its confidence intervals are accurate for everyone.
So it's kind of like leveling the playing field.
Yeah.
Making sure that the model isn't making, overly optimistic or pessimistic predictions for certain groups.
Exactly.
That makes a lot of sense. You also mentioned logistic losses.
Right.
And those are used for classification problems, right?
Yeah.
Like deciding if an email is spam or not.
Yeah, like yes or no situations.
Okay.
And they can be used for debiasing as well.
Okay.
So let's say you're using a model to predict whether a customer will click on an ad.
Mm-hmm.
A logistic loss can help ensure that the model's estimated probability of clicking is unbiased across different demographics,
Okay.
even if the original data contains some biases.
So it's not just about making accurate predictions.
Right.
It's also about ensuring that those predictions are fair
Exactly.
and don't perpetuate any existing biases.
Yeah, it's about fairness and accuracy.
It sounds like gradient equilibrium combined with these different loss functions is a pretty powerful tool for tackling these issues.
It really is.
But does the paper go beyond the theory
It does.
and show how these techniques actually work in the real world?
It does. There are several compelling case studies.
Okay.
One that really stands out uses the MIMS-3 dataset.
Right.
Yeah, huge collection of electronic health records.
The one they used to predict patient length of stay.
Exactly.
Oh, okay.
So they started with an existing model,
Yeah.
but they suspected it might be biased.
Okay.
Instead of retraining the entire model,
Mm-hmm.
which can be very time-consuming and expensive,
Yeah.
they used online learning with a specific type of logistic loss to adjust the predictions in real time.
So as new patients came in,
Yeah.
the algorithm was constantly learning and fine-tuning its predictions to minimize bias.
That's right. And the results were really impressive.
Okay.
They were able to significantly reduce bias,
Wow.
leading to much more accurate and equitable estimates of patient length of stay,
That's amazing.
which has huge implications for hospital management and resource allocation.
Yeah. It's incredible to see how these theoretical concepts can have such a tangible impact on real-world problems.
Yeah, it's really cool.
Now, beyond the MIIC dataset,
Mm-hmm.
what other real-world applications did the paper highlight?
So they also explored examples involving Bradley-Terry models.
Okay.
These models are commonly used for ranking things,
Okay.
like chess players or sports teams.
So instead of predicting a number like length of stay or probability of clicking an ad,
Right.
we're now talking about predicting an order.
Exactly who comes first, second, third, and so on.
Okay.
And the paper shows how online learning with gradient equilibrium can be applied to these ranking problems as well.
Okay.
This gives us insights into how rankings change over time as new data becomes available.
So I'm already thinking about how this could be used to analyze like social media trends or predict which products will become popular.
Exactly.
Yeah.
There are so many possibilities.
But before we go too far down that rabbit hole, I want to loop back to something we discussed earlier.
Okay.
Regularization.
Yeah,
Can you remind us why that's so important,
of course.
especially in online learning?
So regularization is like setting up guardrails for your algorithm.
Okay.
It prevents the algorithm from becoming too sensitive to the most recent data points.
So it's like preventing it from overreacting to the latest fads or outliers?
Exactly. It helps to find that sweet spot between flexibility and stability.
Okay.
The algorithm needs to be able to adapt to new information,
Right.
but it also needs to be robust enough to handle noise and fluctuations in the data.
And how does this tie into gradient equilibrium?
So the paper shows how regularization actually affects the dynamics of gradient equilibrium.
Okay.
It demonstrates that by carefully choosing the right regularization techniques, we can guide the algorithm towards a stable and balanced state.
Okay.
Even as the data continues to evolve.
It sounds like regularization is an essential ingredient for making sure that these online learning algorithms are both accurate and reliable.
Yeah, absolutely. It's all about finding that balance.
Over the long haul.
Exactly.
We've covered a lot of ground in this deep dive.
We have.
We've gone from the basic idea of gradient equilibrium to its role in debiasing predictions, its connection to different types of loss functions, convex analysis,
Right.
the challenges of step sizes.
Yeah.
I feel like I've gained a whole new appreciation for the complexity
It is complex.
and the beauty of online learning.
It is beautiful.
Where do we go from here?
Well, there are some more nuanced aspects of gradient equilibrium that we haven't really touched on yet.
Okay.
The paper delves into its connection to concepts from convex analysis,
Okay.
which might sound a bit intimidating.
Convex analysis. Okay.
But it's actually quite fascinating.
I'm intrigued.
Yeah.
Let's dive into that in the next part of our deep dive.
Oh, sounds good.
We're back for the final part of our deep dive into the world of online learning and gradient equilibrium. Before the break, you mentioned something called convex analysis, and I have to admit, it sounds a bit intimidating. Can you demystify it for us?
Of course, convex analysis might sound scary, but it's really just a branch of mathematics that deals with certain types of functions. You can think of a convex function like a bowl.
Okay.
It has a single lowest point, which makes it easier to find like the optimal solution.
Okay, I'm starting to get the picture. So how does this bowl analogy relate to online learning and gradient equilibrium?
Well, a lot of machine learning problems, including online learning, involve finding the minimum of a function.
Okay.
That's where the bowl comes in.
Yeah.
And the paper explores how certain conditions on the gradients of these functions, like strong monotonicity or coercivity,
Okay.
can guarantee that the algorithm reaches gradient equilibrium.
Now you're throwing out more technical terms.
Right.
Monotonicity, coercivity.
Yeah.
Can you unpack those for us, non-mathematicians?
Imagine you're climbing a hill. If the hill gets steeper as you go up, that's like a monotonic function.
Okay.
Coercivity is a bit more technical, but you can think of it as a measure of how smooth the hill is.
So these conditions, monotonicity and coercivity, are kind of like checking the terrain to see if it's suitable
Yeah.
for reaching that balance point, that gradient equilibrium.
That's a great way to put it.
Yeah.
They provide theoretical tools to analyze the behavior of these online learning algorithms and understand, under what conditions they're likely to reach that desired state of equilibrium.
So it's not just about designing the algorithm, it's also about analyzing its underlying mathematical properties
Exactly.
to make sure that it's going to work as intended.
It's about understanding how the math connects to the real world.
Now, there's one more thing I wanted to ask about, something we haven't discussed yet, step sizes.
Okay.
I remember it being mentioned in the paper, but I wasn't quite sure what it meant.
So step sizes are a crucial parameter in online learning. They control how much the algorithm adjusts its knowledge with each new piece of data.
Okay,
Like-
it encounters.
So if the step size is too big,
Yeah,
the algorithm might overshoot the target,
right.
like taking a giant leap forward and missing the mark.
Exactly.
And if it's too small, it might take forever to get there.
Right, like taking tiny baby steps.
Yeah.
Exactly. And the paper discusses the challenge of dealing with arbitrary step sizes,
Okay.
especially when those step sizes are like decreasing over time.
Why is that a challenge?
Yeah.
Doesn't it make sense for the algorithm to become more cautious as it learns more?
It does make intuitive sense, but it makes the mathematical analysis a bit trickier.
Okay.
Remember, our goal is to achieve gradient equilibrium, which is about finding that balance point in the long run.
Right.
But if the step sizes are constantly shrinking, the algorithm becomes less and less responsive to new information over time.
So it's like the algorithm's getting more conservative
Yeah.
as it gathers more data,
Right.
which makes it harder to be sure that it's really converging to that equilibrium point. Exactly. The paper explores ways to adapt the analysis to handle these shrinking step sizes and still guarantee that the algorithm is on the right track toward equilibrium.
This has been an incredible journey. We've explored gradient equilibrium from its basic definition to its role in addressing bias, its connection to loss functions and convex analysis, and the challenges of step sizes. I feel like I've gained a whole new appreciation for the complexity and the beauty of online learning.
I'm glad to hear that. And remember, this is just the beginning. There's so much more to discover in this field.
So for our listeners who are eager to keep learning, what would you suggest as a next step?
I'd encourage them to explore some of the real-world applications of online learning. There are fascinating examples in areas like recommendation systems, financial modeling, and even self-driving cars.
That's a great point. Online learning is all around us, shaping our digital world in ways we might not even realize. So the next time you see a personalized recommendation or hear about a new AI breakthrough, remember that gradient equilibrium might be playing a role behind the scenes, helping those algorithms find that delicate balance between learning and stability.
Absolutely.
Right.
And who knows, maybe one of our listeners will be inspired to make their own contributions to this exciting field.
Thanks for joining us on this deep dive into gradient equilibrium. Until next time, keep those minds curious.